going to introduce you Tony Seale, and his talk title is Embracing Complexity, Building Your Knowledge's Organization Graph. Let's give a round of applause for Tony.
Hello, everyone. Sorry about the delays there. And now... Sorry, 1 second, more problems. I think... Okay, this is looking better. I think that version got corrupt. Okay. All right. Let me begin by asking you a question. Do you think that progress moves in a straight line? Well, I think quite obviously it doesn't. In fact, progress comes with sudden shifts and changes. So imagine yourself as a hunter-gatherer as the neighboring tribe first began planting their crops, or then again as a farm laborer as the first mechanized plough trundled into your farm. These are moments of great societal change. This is where upheavals happen, where paradigms shift. And we're at one of these moments right now. So, just kind of casting your mind a little bit into a future, if you're working within an organization, imagine being able to have all of the knowledge that's within that organization compressed. All of the documents, every single piece of data, intelligence, plus all the information that's compressed from the web, all condensed down so that you can ask far-reaching questions across any of the information within an organization. And this might sound like a kind of science fiction fantasy, but my prediction is 5 to maybe 10, 20-year time frame at the max. That is what every organization is going to have to do as standard. So I've been thinking about this for quite some time now, and I'm going to hit you within the next 30 minutes with some relatively big ideas. If you find that that's a bit kind of overwhelming or anything, then check out my articles on Medium, or come follow me on LinkedIn and join in the conversation there, and that'll give some background to what we're doing. So, okay, where do we start? Well, if you're an organization, then you start with where you already are, which is basically the data that your organization has already collected. The key here is not to get too mesmerized by the sudden technical tectonic shifts in technology. If we are at the beginning of one of these exponential curves, things are going to start moving very, very fast, very, very quickly. And for a non-big tech organization, it's probably going to feel a little bit scary. So the part that I would point out here is that really AI, the algorithms themselves, they are just like the shining tip of the AI iceberg. And anybody that's working with it knows that underneath that, under the surface, under the water, is this murky world of data pipelines, massive, vast data sets, data cleansing. And if you're not an organization that is a giant platform, you can't just take your data and pull it off of the web. But actually, most organizations already have a massive asset, which is the information that they've already accumulated. We're actually like beggars sitting on top of a gold mine because they've got the experts in there who understand the data, and there's all of the databases, all of that rich information. So I'm going to try and give a few clear messages, and the first clear message is don't get too mesmerized by the AI. First of all, concentrate on one task, which is connecting and consolidating all of the data that you already have. But if you're an organization of any size, your data is in a complete mess at the moment. It's fractured and fragmented. It's split across literally thousands of different databases in large organizations. We're kind of stuck in this vicious loop where a new market opportunity arises, so the answer to that is to create a new application. But each time that you create a new application, you've added a whole new set of schemas and database tables, and now those have got to be linked back in order to be able to take a holistic view of how your organization functions as a complete system. So each time that you do that, you've just increased the fragmentation by a small fraction, and over time, these fractions add up, and they add up, and they add up, and in a large organization, it can now take, well, it can cost, I've heard cases anyway, where it can cost millions of dollars just to get a couple of extra fields added onto a report, because the information is just being drawn from so many different systems in so many different places. Okay, so what's the answer then? Well, I'll tell you what the answer is not, and that is building one big central data warehouse, data lake, even central fancy knowledge graph, which I'll go on to talk about. Because this is what we've been trying for the last 40 years, and it simply doesn't work. And this is kind of not surprising, because within these big organizations, each application here in itself represents a very complex system. There's a whole team of people working around it. It's got hundreds of tables. It's got all sorts of logic going on within it. If you think about it, there's simply no way that you can collapse all of that complexity into one central store. And to be clear, this is not a technology problem. Yeah, sure, you could create some big Hadoop data lake to do it. This is a people problem. You can't take all of the complexity, all of that knowledge, and get one central team to collate it into one place. Time's ticking on this one. This is time sensitive. The AI revolution is beginning to kick off. The exponential curve is kicking off. Organizations need to pivot fast away from this centralized model. And we've got a new model now. It's called the data mesh. It's got a fancy, trendy name. And it prioritizes and talks about decentralized data ownership, domain-specific data products, and a self-service data infrastructure. And that's great, but beware. So many companies at the moment are beginning setting up their data mesh projects, but if you simply set up your data product without any emphasis on data integration, then all that you're basically doing is repeating the problems that failed with the data lakes. You've just got a distributed data lake now because you haven't actually faced up to the data integration problem. The data integration problem is the elephant in the room. That's the hard part. The hard part is being able to connect your information together, joining up all of those dots. The hard part is getting everyone to agree on a common set of semantics, not having 100 different schemas for things. So this is key message number 2. You need to do a decentralized data integration, but it needs to be a data integration. You need to actually connect information together. You need to actually agree upon a common set of semantics. And luckily, we don't actually need to reinvent the wheel here, because this is where knowledge graphs come in. So if we want to face the data integration problem head on, then we need to actually connect information together. We need to take the relationships between the data items as seriously as the data items themselves. So, as Leonardo da Vinci said, learn how to see, realize that everything connects to everything else. It's actually in the relationships between things that's where the meaning comes. Data existing on its own, in isolation, has no meaning. It's all dependent upon the context. And the way that most of us are familiar with storing data at the moment is in relational databases. So we have lots and lots of relational databases. We have then data warehouses that are based upon that format. We will dump our data in Parquet files. And relational databases are based on a branch of mathematics called set theory. And in set theory, the sum of the data, the value of the data is simply the sum of the parts within it. But a different way of storing your data is within a graph, into a knowledge graph, which is based upon a different branch of mathematics called graph theory. And in graph theory, the relationships are treated as first-class citizens. They're as important as the data items themselves, and it's really not too complicated. Basically, within a graph, you've got nodes, which sometimes are called vertices, and you've got edges, and edges link nodes together. It's kind of as simple as that, really. And graphs have got what I call a structured scruffiness to them. They're very expressive data structures that are able to capture much greater levels of complexity than other data structures that we're familiar with. So we can take a table expressed like this, and we can easily transform that into a graph. Or perhaps you're familiar with tree-like structures, for instance, JSON, or if you're really old, XML, then these two can be converted into a graph structure. We can even include cycles within graph structures for modeling the nonlinear stuff. And they're sufficiently complicated, they're sufficiently expressive that we can include them as little islands within text and images, kind of grounding these things with specific pieces of data. And I'll come back to that towards the end. But the key point I want to make here is it's not like these data structures go away of tables and trees, but the graph then can sit on top of them, joining them all together into one common form. Graphs are a data structure that can face the data integration problem head on, because they're building connectivity into their very nature. So that's my third message. Graphs are a data structure built for data integration. But you'll hear people say, well, graphs are complicated, the semantic web is dead, we already tried that idea, blah, 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 blah. Right? Well, wrong. Let me tell you about JSON LD. So any developer these days is familiar with JSON. It's a pretty simple syntax. And JSON LD takes this structure and adds a few special properties to the top of it. First of all, we get the at context and the at type. And these two give semantics to the data structure. So they point back to a schema, and I'll come into more details on that in a second. And then here we have the at ID. And this seems like a small thing, but with this, I'm now assigning a unique URL to this data item. So every data item is getting a unique URL. Why is that important? Well, because now, if I want to say that Jane Doe has a colleague of John Smith, I can connect the two together using their URLs. These resolvable URLs are just like web pages out on the web. If I click on one of them, I get the data back. And suddenly we've got a distributed graph. But the key kind of revelation that I want to point out to you here is that over 44% of all web pages on the web now contain these islands of JSON-LD. So that's almost half of the web with JSON-LD embedded upon it. This is not like rocket science or PhD students that are doing this, just normal web developers who are trying to boost up their SEO ratings of their website. If you put some information on there about a product that you've got, the web developers are including in this little tag of JSON-LD in all of those web pages. Half of the web. We talked about returning back to the context here. So this is a kind of key revelation, because each of these islands of JSON-LD, pretty much all of them, they all point back to schema.org. And schema.org is put together by Google and Microsoft and the other search engines. And it has a common set of schemas for the things that people mostly search for on the web. Products, flights, bookings. Here we take the example of a recipe. So schema.org has got a definition of what a recipe looks like there, published on the web with ingredients, cooking time, etc., etc. And then in here, this example here, the BBC, on their website, they're putting up a recipe, and they reference back to the schema.org context out on the web, and they provide information for their recipe. And then if I go in to Google or Bing and I search for a spicy bean burrito, I get back some very precise results. Now, why am I getting back precise results here? Because I'm searching the Google knowledge graph. So I'm not just searching through nuanced, fuzzy text. I'm searching through precise data, because Google, just like it's crawled the web in order to do the searching, it's crawling the web and it's finding these islands of JSON-LD and it's storing them in its knowledge graph, so that when I put in spicy bean burrito, I could put in spicy bean burrito that takes 5 minutes to cook and is not too spicy. You know, I can do now really precise queries with this. Next key point. This is data integration working on a limitless scale. This is a scaleless architecture. Can pop up a new website here now on my laptop. I could embed JSON-LD in it and map into this schema, and I've just added data into the system. And what have they done here? They've inverted the cost of data integration. So we're used to the cost of data integration being upon the consumer of that information. It's that centralized team that has to do all of the work of mapping and conforming the data. But what the search engines are showing here is actually you can put the cost of data integration upon the person who is publishing the data, and that's what makes it a scaleless architecture. So things are getting more concrete for us now. We know that in order to survive the exponential curve of the AI revolution, large existing companies need to consolidate all of their data assets. We know that's hard to connect all of the data, but we've got a model that is proven to be doing that out on the web. So why not just take that same model and apply it within the context of your own organization? Schema.org is an open source project. You can just go and download it off of GitLab. You get all of their schemas in there, and you can stand up that server behind the firewall within your organization. So now it's your schema.org. I would advise taking their base types as your kind of starting model, but you can begin to develop your own particular semantics that are related to your own particular business. So if you're a bank, there'll be trade and risk. If you're a rail provider, it will be tracks and trains. If you're a hospital, it will be patients and beds and medicines. Whatever it is that is specific about your business, get frosty on that, get sharp on it, and get those definitions embedded into your own personal schema.org. And when you're doing that, stick as close to the business semantics as you possibly can. Get the business people involved in it. This is not just an IT thing. You want the actual people which are using the language. You want the structure of the data to reflect how people are talking about their business. Now, if you go back and propose this idea within your organization, you're likely to hear kickback. Oh, we can't have a base foundational model. We've tried that in the past. It's failed. The answer to that is we're in the middle of a paradigm shift here. Time is ticking. Things are changing. The rules change in a paradigm shift. Organizations have to connect and consolidate their data, or they're going to go out of business. It's really as blunt as that. Okay, so we can return to the data mesh now, because now that we've got JSON LD, and now that we've got schema.org, we can think about all of those kind of crazy spaghetti of different applications and databases. So in a large organization, just to give you an insight, there'll be somewhere between 5,000 to maybe 100,000 separate applications and databases. Each one of those is going to have thousands of different tables in it. Each table has got hundreds of different columns in it. So this vast, vast complexity. And at the moment, they're woven together with a spaghetti of different technologies. People are sticking stuff on message buses. They're dropping CSV files here. They're sending XMLs there. This other guy's set up a RESTful web service. It is a nightmare. You just kind of ask any IT department show me the network architecture for your department, and you struggle to fit it on a page in any meaningful sense. Okay, but now we're talking about something slightly different. We're saying, well, each application, we want to invert the cost of data integration. It's on you to publish the information in JSON LD. So it's a data product, but it's a linked data. It's a data mesh, but it's a linked data mesh. This application is publishing its fraction of the graph. It's using URLs in order to identify each data item. This application is publishing its fraction of the graph using URLs to identify them. And when one item links to another, you just reference the URL of that data item in order to connect it together. What's more, these data products are semantic data products. So they are referencing the well-known semantics which are defined on your schema.org. So if two applications are publishing similar information, then they, where possible, at the base level, they're using the same well-understood semantics. So this is the fourth message here then, which is use JSON LD and your schema.org to begin the process of connecting all of your data in a decentralized way. And when you've got that distributed graph, now you have your knowledge graph. But beware, remember, we're not creating one big central store here. This is the next pitfall that people can fall into. I have my knowledge graph, it's one big database. That's a mistake, one that I've made myself in the past. If you try to load all of this into one big graph database, you end up with these massive trillion-edge triple stores, which are flaky and very difficult to work with. But you don't need to do that. When you browse the web, it's not like you load the whole of the web into your web browser. So just because all of your organization's data is connected together in one distributed graph, you don't need to download it all into one database. You have a particular use case, and you download the chunk of the graph that you need, pre-connected, pre-integrated, into a given triple store, into a given knowledge graph, in order to meet that use case. So each team could have its own knowledge graph. each user could potentially have its own knowledge graph, all feeding off of this one connected, distributed graph of connected information. The phrase I like to use here is, within your organization, let 1,000 knowledge graphs bloom. And this gives you a better architecture anyway. It's much more scalable. You can add and remove knowledge graphs as are needed. But obviously, we want to, still at the level of the whole organization, of a complete system, we want to see the whole thing connected together. And to do that, we use a pretty old pattern, which is called the data catalog. And I'll be honest with you, data catalogs have had pretty mixed success. But what we can do here is we can apply the same pattern of data integration cost to the idea of the data catalog itself. So basically what we say is each semantic data product, as part of yourself, publish a catalog of the data that you have available. What is it that you've got to offer the business? This application must be here for a reason. We're pumping a load of money into you being here. What are the data sets that you have got to offer everybody else? And we have a definition of what a data set is in our internal version of schema.org. You don't need to write your own one. There's already perfectly good ones out there on the web. And everybody publishes their data catalog according to this standard. So now the central company data catalog only has to hop around all of the data products that have been registered, and it can collate them all together. Again, it's its own little knowledge graph. This knowledge graph is just simply focused on collecting all of the lists of data sets together. Okay, so we've been through quite a lot in a short period of time here, but we now have what I call the semantic layer architecture set out. So within the semantic layer architecture, I'll just quickly run over it again. We've got your schema.org, which is providing the model for in the business semantics of whatever your particular business is in. Then you've got all of the applications publishing semantic data products according to these linked data standards in JSON LD, and that creates your linked data graph. And then finally, pulling all of that together, you've got the data catalog. Okay. You've all been very patient. We've done the submerged part now. We've got the kind of the semantic layer gives us the data pipeline part. We can move on to the shiny AI algorithms. We've got the engine, so let's inject the rocket fuel. So, unless you've been asleep for the last 6 months, I'm sure you've heard of GPT. But let me just kind of refresh your memory of what's going on with GPT. GPT is a large language model, and it's large because it has basically downloaded all of the text off of the web, and it's compressed that. So it's learning off it using the transformer model, doing next token prediction, saying what's going to come next. And this is a nuanced, fuzzy sea of natural language. It's everything everyone's kind of blurted out and put on all of those different web pages. And that's very powerful. It gives you enormous opportunities, but it's also fuzzy and it's kind of unreliable. But wait a second. The common crawl has downloaded all of those web pages, but half of those web pages have got these islands of JSON LD in them, right? So half of these web pages have actually got chunks of data in them. And from my experimentation, GPT, not all of the large language models, but GPT, for instance, is using those islands of JSON LD. Why? Well, why wouldn't you? You've got all this text, and now sitting right next to it, you've got some concrete, precise facts. I mean, don't get me wrong, people put bad data into their JSON LD as well, but it's a lot more specific than the nuanced, fuzzy sea of data. We've got these islands of JSON LD, and here's the cool thing, right? Turns out you can reverse the polarity on this. You can actually then use its knowledge of JSON LD and the facts that are bedding in there, and you can turn that round and connect it back into your own internal data. So basically, what we're saying is, out there on the web, you've got this structure going on where we've got all of these HTML pages, so we've got all of this textual information, we've got structural data in the form of JSON LD, and then we've got large language models which have taken it and they've compressed it all. So why not take that whole setup and have it internally within your own organization? You've got all of your own documents, you've got all of your data, and with the semantic layer, that's now all accessible via your data catalog. Get an instance of a large language model, like Llama if you haven't got very much money, or stand up GPT on an Azure server in your private cloud if you've got it, and you've got the same infrastructure there. So now your organization is able to put in a natural language question that is going to take the compressed information and knowledge of everything that's on the web, and then it's going to go out to your semantic layer, and it's going to say, okay, what kind of concepts are we talking about here? Right, what have I got in the semantic layer that's relevant to that? What documents have I got loaded up? What data have I got that I can get in and I can pull in? And then this information, because it's in a graph, gets kind of merged together. Because remember, graphs are all about connectivity. So information that is knowledge that's coming off of the compressed web then gets connected into information that you're holding locally behind your firewall. I call it the working memory graph. Basically, there'll be a task at hand that you want to complete, or one of your users wants to complete, and that question will come in natural language, and then you're going to use the large language model's common sense understanding of the world and its compressed information off of the web. But then you can't quite rely upon that because large language models hallucinate, they can be inaccurate. But you're using the working memory graph to kind of ground that into reality. So you basically get it to use well-known URIs in the JSON LD that comes back to it. You basically say to the large language model, give me your data in JSON LD, and because it's been trained on so much JSON LD, the large language model can respond to you with the JSON LD graph. So your question comes in natural language, a JSON LD graph comes back, and that JSON LD graph uses well-known URIs to identify the entities that it's recognized. Like using Wikidata is a good, it's a large open source knowledge graph, and that's a good idea to use that. And then you can map from those well-known URIs into matching items within your own internal data. And there's a lot of research going on in this space. I did some analysis of the submissions around knowledge graphs, which unfortunately, because of the problems we had just now, I can't go into that. But let me quickly leave you with this thought. Is it possible that, in fact, we may be able to collapse this even further? We've got graph neural networks at the moment, which are a powerful way of understanding graphs. And at a naive level, you could say that a transformer could be converted into a fully connected graph where the word parts are connected with an intention weighting. Don't get me wrong, this is a naive interpretation of that, but I recommend following some of Michael Bronstein's work where he talks about finding these deeper geometric patterns, because this is super exciting. If we can actually collapse text and data down, then we're there. Then we have this kind of one compression of every organization's data. So, as I say, it's quite a lot to take in, but please come follow me on LinkedIn if you're interested in this sort of thing. I'm passionate about this because although we're in this very exciting period, super exciting period, I have this fear in the back of my mind, which is that there's a possibility of our rich ecosystem of companies collapsing down into a few small, large, uber-powerful AIs. And I think by sharing information and learning and using patterns like this, hopefully we can create a future where there's diversity and AI is open for all. Thank you.